Hello, I'm Greg White, a distinguished technologist at CableLabs, and this session is going to talk about the L4S technology, which stands for low latency, low loss, scalable throughput. This technology, L4S, is intended to address an issue that relates to network congestion and network latency. And it's well known that latency increases when a link is congested in the network. But it's not for the reason that a lot of people may think it is. It's not because there's too much traffic for the available bandwidth. And what I mean by that is that the majority of traffic on the internet today is congestion controlled. Which means it adjusts its sending rate based on what it detects is the available capacity or available bandwidth of the path from the sender to the receiver. So all of the applications, or essentially all the applications, are adjusting their rate to try to fully utilize the available capacity without sending too fast. Another way to say that is latency isn't increasing because, quote unquote, latency increases with offered load. That's the queuing theory 101 kind of explanation of the correlation between latency and congestion or load on the network. And in real life, there really is no such thing as offered load. Again, applications are not just traffic generators in a laboratory that are sending at a particular rate that's been configured in the application. They're adjusting the rate based on what they detect from the network. So the real reason that congestion increases the latency in a network is because the congestion control mechanism that is used by applications is ossified. It's not been able to evolve significantly since the early days of the internet. And the reason for that is back in the mid 80s, the internet suffered a congestion collapse because applications actually weren't detecting the available capacity and adjusting their sending rate, and that caused a collapse in the early internet. And congestion control was designed at that time to solve that problem. And the main algorithm that came out of that work in the mid to late 80s was an algorithm called Reno, and was implemented in the TCP protocol. And everyone adopted that, which was great. That solved the congestion collapse issue. But it created a legacy where everything from that point forward had to be Reno friendly. Actually, the term that was used in the industry was TCP friendly, because when you said TCP, you meant Reno. That's was the algorithm that was implemented. And so anything new, any evolution of that algorithm had to coexist with everything else that was using Reno. And so it had to respond in a very similar way to the detection of congestion and adjust its rate in a very similar way. Otherwise, things would get out of balance, and either the new application would stomp on all the other applications that were using Reno, or vice versa, the new application wouldn't get very much capacity because it would back off more aggressively and reduce its sending rate. So that was one piece of the Reno legacy. The second piece of it is that network equipment got optimized to provide great throughput, given that the applications were using TCP Reno. And so they intentionally designed network gear in order to make sure that throughput was optimized for Reno. So a little bit more background to fill out the picture about congestion control here, what it's trying to do, how does it do it. So this is kind of a toy example called a dumbbell topology, where we've got some senders on the left-hand side. Each sending device is connected to a shared node with a 1 gigabit per second link. And then we've got some receivers on the far right-hand side. They're also connected to a shared node via each one with a 1 gigabit per second link. And then these two shared nodes in the middle are connected to each other with a 100 megabit per second link. So the question is, and there could be any number of senders and receivers. I list it here as N. How does each sender know how fast to send its traffic? Each sender can't learn. There's no protocol for a sender to learn that that bottleneck link in the middle is 100 megabits per second. Nor does each sender know how many other senders there are that are trying to share that bottleneck link. And so the way that the senders manage this in the internet today is that they adjust their sending rate using a congestion control algorithm. And so in effect, it's probing for the available capacity in the path, kind of increasing its sending rate until it senses that there's some congestion, and then back off a little bit. Because senders and receivers come and go, applications need to send files, and then once the files are sent, they discontinue sending. So the number of senders and receivers is constantly changing. So the number of flows or connections that are sharing that bottleneck link is also constantly changing. And so each sender is periodically, or actually continuously, trying to ramp up its sending rate to see, is there more capacity available that I can send faster? And then looking for some kind of a signal of congestion and backing off a bit. And if there's more congestion, backing off more and more. And so again, adjusting its sending rate based on what it senses is the available capacity. Now, the existing congestion control algorithms, so Reno is the one I mentioned before. The evolution of Reno is called cubic, but behaves in a very similar manner for the reasons I discussed a minute ago. Those algorithms cause large latency spikes and packet loss as part of the mechanism that they use to try to detect the capacity. The gist of it is they end up sending too fast, causing a queue to build up in the network. In this diagram, it would be in that first shared node that all the senders are connected to. A queue would build up at the egress of that node as traffic is trying to get out onto that 100 megabit per second link. And when that queue builds up so much that there's no more space to send, to store packets, additional packets that arrive have to get dropped. So that's packet loss, and that large queue that has built up in that network element is causing latency, because any packet that arrives and goes into the end of the queue has to then wait until it makes it all the way to the head of the queue before it can get transmitted. And that can be hundreds of milliseconds of queuing delay. And when there are no senders, there are no congestion control algorithms that are running in this network, that queue will be empty. And if you send a packet, you'll get a very quick turnaround, so very low latency. But when a congestion control algorithm starts up, fills up that queue or that buffer, now if you try to measure the latency, you get a very high latency. So you can see latency varies over time as applications start and end, and as the congestion control algorithms are adjusting their sending rate to try to fully utilize the path. All right, a little bit more on this Reno legacy and why it's keeping buffers full. So Reno and by extension the cubic algorithm rely on the network to provide those deep packet buffers and then drop the packets when the buffers overflow. And so it's the packet loss is what the TCP or Reno or cubic algorithm is detecting to know that it was sending too fast. And so it, again, ramps up its sending rate until it sees packet loss, and then actually pauses a little bit to let some traffic drain out of those network buffers, and then it starts sending again and filling up the buffers again. And so the graphic on the bottom right shows the evolution in time of a TCP congestion control algorithm, showing how it ramps up, causes packet loss, backs off a bit, and then ramps up again. And so the side effect of this is any application that's sharing that bottleneck link and sharing that bottleneck link buffer is suffering from the latency and jitter and packet loss that these congestion control algorithms are introducing. So even a low bitrate application like voice over IP or an online game that's not trying to fully utilize the capacity of the link, it still suffers from all the latency jitter and loss that TCP and QUIC and these congestion control algorithms cause. And of course, again, those applications come and go. So sometimes the network is not carrying any of those, or the bottleneck link in the network is not carrying any of those congestion controlled applications, and so an online game can get great performance. But then, as soon as a file needs to be transmitted on the network, you get these spikes of latency and packet loss. All right, I've used the term bottleneck link here a couple of times. And probably worth talking a little bit more about how that's important here. So the bottleneck link is, if you think of the path from any sender to any receiver, it could be a client and a server, or it could be two clients that are sending peer-to-peer traffic. The bottleneck link is the link along that path that has the least available capacity. So the most common bottleneck links are in the home network, so the Wi-Fi local area network in particular, and on the access network, where the access network is designed in order to provide a specific data rate to the customer. And the expectation and design of the ISP's network is that their core network isn't the bottleneck, it's the configuration of the access network that is. Now, thinking back to that congestion control algorithm that's ramping up its sending rate and causing this queue to build up, that queue is building up at that bottleneck. So it's not building up somewhere else along the path. It's just that link where the capacity is even temporarily fully utilized, where the sender is trying to send as much as it can, and it's running up to that capacity of that bottleneck. And so that's where the packet buffering and the latency and loss happens in the network. So what's the solution? So this is an end-to-end problem. As we've discussed, it involves the congestion control algorithm in the application or in the sender, and it involves the network bottleneck. How much buffering does the network bottleneck provide? And how does it give a signal to the congestion controller that the congestion controller in the application is sending too fast? So the root cause here is there's insufficient feedback from the network to the applications to signal when congestion occurs. And so the solution is an end-to-end solution, and it's referred to as L4S, low latency, low loss, scalable throughput. And it provides high fidelity congestion feedback from the network bottlenecks to the applications. And it involves the applications implementing a new congestion control algorithm that can understand that feedback, adjust their sending rates with much better precision to fully utilize the link capacity without causing latency and packet loss. And then the slide mentions also latency isolation. That's a key piece of the incremental deployment strategy for this. I mentioned that we've got this legacy of Reno friendliness or TCP friendliness, where any new proposed congestion control algorithm has had to deal with the fact that everyone else is using Reno or today Cubic, and so you've got to do the same thing in effect, or largely the same thing that Reno and Cubic do. Part of the L4S architecture is a solution to that that allows us to incrementally deploy L4S and one at a time, application by application, and the applications that implement it can get the benefit, and the ones that don't aren't penalized. They still get the same performance they do today, and that's by isolating the two types of traffic, two types of congestion control in the network bottlenecks that support it. All right, so a little bit more detail on L4S. What is it? So it is an architecture to enable this new congestion control mechanism for capacity seeking applications. So that means applications that are wanting to increase their sending rate to whatever the link can support, and then backing off and adjusting to make space for other applications to share that capacity in a fair manner. It can be used by any application. So TCP and QUIC are great examples that could use it. Also, real-time applications that use UDP, maybe they're using the RTP protocol to timestamp the real-time packets. Those can use this mechanism as well. It solves a scalability problem. So a single flow can actually ramp up to utilize to fully utilize a multi-gigabit per second link, which is a problem with the existing Reno and Cubic algorithms today. It solves that buffering and delay problem that exists with existing TCP and QUIC congestion control algorithms. So here, L4S can maintain a sub-millisecond queuing delay without causing packet loss and fully utilizing the link. And it can coexist with the classic TCP and QUIC congestion controls like Reno and Cubic. And that involves that isolation piece that I mentioned. Why is this important? So this technology is perfect for applications that really do want to send at high data rate and get consistent ultra low latency and near zero packet loss. In the past, it has commonly been believed that that high throughput and low latency are mutually exclusive. An application can either get low latency or get high throughput and not get both at the same time. L4S breaks that and allows high data rates and ultra low latency. So it's an ideal solution for cloud gaming, cloud VR and AR applications. Also a fantastic solution for high quality video conferencing. But even beyond those applications that we kind of think of as being latency sensitive, it's beneficial for any application that is latency bound today. So general HTTP traffic, so web traffic and applications that use HTTP as part of their the way they fetch information from the network would benefit from adopting the L4S congestion control mechanism. It's been defined by the Internet Engineering Task Force. It's published as a series of RFCs. So the three RFC numbers are listed here. It was published early this year in January. All right, a little bit more on the details of L4S. So as you may have gathered by now, it's a closed loop mechanism. So congestion control in general is a closed loop mechanism where the sender is introducing some sending behavior, some traffic into the network. The receiver is receiving that traffic and then sending some kind of a feedback to the sender that the sender interprets in order to adjust its sending behavior. And so the same is true here, but instead of using packet loss as the identifier of congestion in the network, it's using an explicit congestion signal in the form of a field in the header of the of each IP packet that flows through the network. So the sender has to implement a new congestion control mechanism that is based on the requirements that are defined in RFC 9331. These are referred to as the PROG requirements. And then it has to identify its packets as supporting L4S via setting a specific value in the explicit congestion notification field in the IP header, so that the network can identify those packets as being packets associated with an application that supports L4S. The network then, the bottleneck link in particular in the network, has to support the ability to provide those congestion signals. And it's an immediate indication of queuing delay on a packet-by-packet basis, using that ECN or explicit congestion notification field to mark specific packets as having a queuing delay that exceeds some threshold. And so now we've got this explicit congestion signal. The sender no longer has to induce packet loss in the network in order to get congestion signals. And since the congestion signal isn't packet loss, it's this explicit signal, the network can provide much finer grained feedback. So it can provide a lot of these signals, whereas introducing a lot of packet loss historically would have been a problem because that's a degradation to the connection as well. So so that's the bottleneck link's role in this. And then the receiver has to be able to receive the packets, look for that explicit congestion notification field in the header, and look for how many of the packets are arriving with just the I support L4S value that the sender put on, and how many of the packets are instead coming in with the congestion experienced flag from the network saying that a queue is starting to form and you need to back off. And so the receiver has to be able to send that information back to the sender via an accurate ECN mechanism. And that can be as part of the TCP acknowledgements. It can be part of the quick acknowledgements. It can be part of RTCP for RTP flows, or it can be a proprietary protocol built on top of UDP. All right. Incremental deployment, I mentioned this already, as a key piece of making L4S feasible to deploy on the internet. And so we need to make sure that L4S can coexist with classic TCP and classic quick and other classic congestion controllers. And there's two ways to do that in the network. A network element can implement what we call dual queue, or actually it's called dual queue coupled AQM, and it's defined in RFC 9332. And that's two equal priority queues for low latency traffic, for L4S traffic, and for classic traffic, so that both congestion controllers, L4S and classic, can do what they need to do to adjust their sending rates. And the L4S traffic can do that without causing latency in its queue. The classic queue has a nice deep buffer that allows Reno and Cubic to get great throughput performance. And the coupling mechanism, which is the sophisticated piece of this technology, provides a consistent congestion signal to both the L4S traffic and the classic traffic that is sharing that bottleneck link, so that both types of traffic adjust their sending rate in an appropriate way and settle in at a fair sharing of the link capacity. So it's not giving L4S high priority, not giving it more capacity. It's giving an equal share of capacity on a flow-by-flow basis to the comparable classic flows. The second mechanism that can be used in a network element implement L4S is what's called flow queuing, where every individual flow that's going into the bottleneck link gets a separate queue, separate independent queue, and then that queue can either provide the classic congestion signals of packet loss when the queue grows to a certain level, or if the flow supports L4S, give it those explicit congestion notification signals. So two mechanisms that can be implemented. And again, this is what we're talking about here is separation. And just to hammer this point home, it's not prioritization. So buffering latency and this problem of congestion control and the interaction between the sender behavior and the network can be solved without invoking prioritization. Priority is orthogonal to this. If there is some traffic on a particular network segment that is more important and should be given more capacity than other traffic, priority can be used in order to do that. So L4S can be implemented in addition to a priority scheme, but it doesn't use priority on its own in order to solve the latency problem. All right, next couple of slides, next 3 slides actually give some examples of the performance that can be achieved with L4S. The first example is support for L4S in the DOCSIS cable modem protocol. The top graph is a classic TCP cubic flow with a basic FIFO buffer in the network. And I'm not going to go through all the details in the graphs, but the high level outcome here is full utilization at 100 megabits per second, but 261 milliseconds of latency at the 99th percentile. Using L4S on the same network setup, again, full utilization at 100 megabits per second, but the 99th percentile latency is dropped by 2 orders of magnitude, down to 2.2 milliseconds. Another test here with 5G RAN using a prototype implementation of L4S from Nokia, and showing experiment using classic TCP and experiment using L4S TCP. And you can see the latency on the top, throughput in the middle, and then the summary on the lower right. 99th percentile latency for L4S, 2.4 milliseconds, classic 480 milliseconds, a 200-fold reduction in latency. Last example, also from Nokia. This is an implementation of L4S on a Wi-Fi access point. And here, classic latency 274 milliseconds, L4S latency 13 milliseconds. In this case, 1 order of magnitude improvement in latency compared to classic. So in conclusion, L4S provides a standardized solution, standardized by the IETF, and work is underway to adopt it in 5G networks. It's already been adopted by cable broadband networks. Wi-Fi gear is starting to support it as well. It can dramatically reduce network latency, in addition, latency variation or jitter, and packet loss for the applications that adopt it. There are implementations available for the congestion control, as well as a number of network implementations. And in terms of where it's needed in the network, we've talked already about this idea of the bottleneck link. So support for L4S is needed at any network bottleneck along the path in order to get the benefit. But other network hops along the path, say core network routers, core network switches that aren't bottlenecks today, they don't need to support L4S yet. If they become bottlenecks at some point, then yes, they need to support L4S as well to get the latency benefits. All right, so that's it for this discussion. Thanks for attending, and thanks for your interest in L4S.